I am happy to introduce Elisa Kagan, who is our speaker of today at our seminar. Elisa is currently at the postdoc position at the Tel Aviv University, studying the E-squared deformations turbidities section 6 thickening revealed in the ICDP deep sea course. Elisa completed her PhD in geology on the multi-site quaternary paleoseismology along the Dead Sea Reef, independent recording by lake and cave sediments. Elisa is currently studying paleocene holes in woods in the Dead Sea shores and the paleoseismology of caves in northern Calabria. She also completed several other projects like Dead Sea levels, chronology, limnology, sedimentology, and climate of the Bronze-Iron Age transition at the Dead Sea. Elisa was awarded by, I would say, too many awards and prizes. I will list just several of them, like Prize in Excellence from the Canadian Friends of the Hebrew University, Women's Zionist Organization and Harry and Margaret Venn Award, Outstanding Student Paper Award at Physics, and many other awards. So please, Elisa.
Hi, thank you for inviting me. So I'm going to talk today about things that we find in the depocenter of the Dead Sea, a new archive available to our community in the past few years since the ICDP drilling campaign that you've probably heard about from Michael and Lisa and Elisa. So I'm going to be talking about mass movement deposits, and as you can see here, this is already like the end of the talk is when I show that they actually more than double. This is being conservative. They more than double the section that we had expected to find, the thickness of the Lisan formation at the center of the Dead Sea. I'm working on the Lisan, but basically the whole section there, all the sediments are more than double than what was expected from what we thought we would find at the center. Okay, oh yes, and of course working with Shmulik Malko in my postdoc at Tel Aviv University. So, a reminder of what the Lisan formation looks like in outcrops around the Dead Sea. Very, you know, in the last glacial lake, Dead Sea was much higher. Here we can see the last glacial maximum. The lake reached 160 meters below sea level 25,000 years ago, and since then has been receding, with fluctuations during the Holocene, between more or less from year to year. Here we can see the rise of the Lisan 70,000 years ago, and the end of the Lake Lisan at about 14,000 years ago. Just a little bit more information on the Lisan. This was the extent of the lake at about 25,000 years ago. At this point, the Kinneret and the Dead Sea areas were connected. Here you can see the Dead Sea catchment area, the Lake Lisan catchment area, very large. Sampling many different geological environments. The tectonic framework of our area, as you can see, along the Dead Sea transform, the Dead Sea itself, relatively high seismicity along the rift and the Dead Sea, faults, many faults around the Dead Sea. Some are active, some are not, some we don't know yet. And the Lisan sediments, of course, the aragonite white layers and the silty dark layers, aragonite forming from the carbonate entering the lake during flooding and forming probably during the summer, the silt also coming in during the floods. sinking to the bottom. And in outcrop, this is what it looks like, mostly laminated, undisturbed deposition, as we see up here, down here, millimeter scale, and then, of course, disturbed layers, breccias, homogenites, folding, very photogenic, and we know it well from the outcrops. Here's some other nice pictures from the outcrops. Now, so earthquakes we know a lot about, more or less, from around the Dead Sea. Studies on plate tectonics around the Dead Sea area, seismicity, different kinds of paleoseismicity, on fault, not so much, off fault seismites. In the field of paleoseismology, as I said, on fault, off fault, correlation to historical earthquakes, how earthquakes affect the basin margins, mostly because we've been studying the margins, how the sediments behave at the margins. Slumping near shore has been touched upon a little bit in the literature, how different sites display different phenomena, how different earthquake or deformations look like at different outcrops of, let's say, for the Lisan or also for the Holocene, and recurrence time of earthquakes. And there's a long list of people who've been working on this, Marco Agnon, Vital, others, Migovsky, etc., and all of this work, the majority of it has been done along the western shores of the Dead Sea. So when an earthquake like this happens, what do we expect to see at the center of the Dead Sea, at the depocenter? How do the deformations look the same? Does it reach there at all? Does the water level prevent deformation from happening? Or actually, nobody had any idea what we were going to see. So from in November 2010 to March 2011, there was the ICP drilling campaign. Cores were extracted, many, at the depocenter as well as in the shallow lake environment. And a lot of work has been done since. Most of the people working on the cores are working on paleoclimate, salt deposition, dust sources, etc. And there are a few people working on seismicity, paleoseismicity. The cores are now in Germany. They're being taken care of there, better than they would be here probably. And this project, of course, got a lot of publicity, especially a specific maybe drying up of the Dead Sea, which was in all the newspapers. Even some people think that the core can actually confirm the book of Genesis. And a lot of people from all over the world are involved in this project. This is just a picture from a recent workshop at Engedi. People from a huge group from Germany, Americans, Japanese, Spanish, and a lot of Israelis are involved in the study. And there's a lot of collaboration, and it's going quite well. Some publications already. And the location of, this is the drilling site of the deep core, the depocenter core. This is the drilling site of shallow core, just in 3 meters water. After a winter of quite a lot of storms and technical difficulties, so after a few months of one very long core from the depocenter and then additional attempts to have other cores there to correlate, to be able to, fill in the gaps of missing parts of the core, decision was made to move to the shallow water because, we think of the Dead Sea as a pretty relaxed place during storms, but it really wasn't. The water was very rough and the drilling was almost impossible. And also on this map are these blue and yellow dots of places, some of the places where paleoseismology studies were carried out in the Lisan and the Holocene outcrops. Here's just this fault map again with the position of the drill sites. So this is the general lithology of the entire core, 465 meters of core, from the lake floor down. Basically, most of the people working there thought we would get about 1 million years back in time, or 800,000 years back in time. And as I said, after even the initial lithology was analyzed, realized that the section was much thicker, and even this 400 in, like, each formation is much thicker than what we know and what we expected to find in the depocenter, and we only reached back much less in time than we thought. So the general lithology is about here 70 meters of saline formation, Holocene. The Lisan formation is from this salt down to here, about 110 meters of Lisan formation, etc., etc. And initial preliminary C14 dating and uranium-30 dating has confirmed this division. And so I'm going to be talking about the Lisan mostly. So from here we have about 110 meters of what we immediately called Lisan type lithology and Lisan formation. According to chronology on the shores, the Lisan was always dated and always called from 70,000 years ago to 14,000 years ago. That's the time of the Lisan. And below the Lisan, there is an unconformity from the Samar formation to the Lisan. So if we go just according to the normal 70,000 to 14,000 year time period that we know, there's actually only 88 meters of Lisan. So this is still low resolution chronology. And what I'm trying to say is that according to the preliminary age depth diagram of the Lisan formation, the Lisan ends at 177 meters depth, even though it looks like it continues all the way to 200. So now the Torps General is publishing the preliminary chronology, quite low resolution of the entire core. Not many dates from the Lisan, unfortunately. So why is this all important? Why is this actually important to know exactly if this is the end of the Lisan, if this is the end of Lisan? It's just a name in some ways. If this is all Lisan type chronology, but when I'm comparing how thick the Lisan formation is on the margins to what I see in the depocenter, and eventually, interpreting this to have mean something, sediment supply, etc., to the depocenter, I have to know if what we see on the margins is actually the entire Lisan, or maybe the lake wasn't really high enough to deposit these missing 10,000 years here, or this much sediment. All right, so if this is the Lisan part from that section here, okay, sorry for the low resolution, and here is the Lisan section from the outcrops, and I want to put them into the same scale. This is really what it looks like. I'm going to put them on the same scale. The Lisan in the core is much thicker. This, as I said, this is dated already quite well by multi-site chronology of about 5 different sites along the western margins of Lisan outcrops. And this is still low resolution dating, and hopefully we will be making it better. So when we compare it, we have about between 88 to 110 meters of Lisan in the depocenter in comparison to 30 or 40 meters along the margins. This is the difference in sedimentation beds. So, okay, I showed you the Lisan on the outcrops. I'm just going to remind you for one reason. This is the same picture I showed you before, but if we would see this beautiful picture only in a core, it would look different. It would be much harder to interpret what's going on and how many events we are seeing. This is just to give you a feeling of, I'm used to working in the field and outcrops, so for me it was a transition to start working on cores and to try to differentiate events when there's not, there's no dates every few centimeters, and even in a event like this, which when an outcrop is obvious, an event that's from here begins as a fold, and then on top of the folds there's rexiation, and this could be actually all one event. You have to look at it even in a larger scale. And when you look at it in the core, it's much harder to interpret. We have these undeformed almost horizontal, almost undeformed lamina here that are hard to differentiate from really undeformed lamina or to know exactly what's going on. So here's just a few examples of outcrops and what they look like in a core. But in general, even in this case, we can see that this is the top, these are undeformed lamina, top of an event, and the event begins here. The time of this disturbance, this deformation, if we want to date it, we date the first lamina that was deposited on top of this deformation event. But in the outcrops, mostly what we see are not such beautiful photogenic things. They are very thin breccias of broken, fragmented aragonite lamina within a silty matrix, small folds, quite small. And we can see the different Lisan outcrop sites. Pratzin, 29 seismites, quite thick. Masada, 21 seismites. Thinner, Tovlan, only one seismite is seen. Mishmar, only 2/3 of the section is exposed there. There's 10 seismites. Beitar, about 35. So this multi-site differentiation is being worked on in a different project. But as we can see, these are the numbers, more or less. And we'll see soon that these seismites in thickness, they make up only about 5 or 10, up between 5 and 10% of the thickness of the entire section here in the outcrops. Here it is. So yeah, Pratzim and Beitar about 10% of the thickness is breccias in fold, Masada 5%, the rest is laminar. And the sediment in the breccias is likely from a closed source, right on the margins. It doesn't really have anywhere to come from. So what do we see in the cores? Here, Michael, I promised you a picture. So this is more or less overview of the different types of Lisan formation in the cores. We have the regular laminated, typical Lisan type lamina. More or less, some of them are, in general, slightly thinner lamina than what we see in the outcrop. It's the same scale, millimeter scale, thickness of the individual lamina. And we see lots of homogenites, and we see coarse sediments and huge folds, obviously part of a fold, and a little bit of faulting. So this is just a general view. So how are we going to, there's many different names for these big folds, and we could call them, in the literature, there's mass movement deposit, mass transport deposit, rapidly deposited layer turbidites. To me, it doesn't really matter. It's just, a name is just a name, and we can call them here mass movement deposits as you like. But I'm going to call this a turbidite. Call it a Dead Sea turbidite because it's not according to, any Buma sequence or any global idea of what's a turbidite, but this is what we see in the Dead Sea, and we're going to call it a Dead Sea turbidite. So this is just a typical one that we see a lot of them in the core. A normal AD. AD is alternating aragonite and detritus, very thin lamina. The base of this event is somewhat erosional. There's very coarse grained sediments at the bottom, graded fragments sometimes in the very dark cap, and then a resumption of the regular alternating aragonite detritus lamina. This coarse base of these turbidites in thin section, we see their sand size and some quartz, calcites, what we'd expect from whatever's available in the drainage basin. Other type of event that we see they don't always have this coarse base, but here is an erosional base, no obvious coarse grains. These lines are not real. They are like this cleaning of the core scraper. And quite, to the eye, looks like a homogenite, and the dark cap, not so prominent. I mean, this is just an example. And this homogenite, of course, is not actually homogeneous, and Elisa is working on those, among many other things, working on that and studying them in detail and showing that they're not really homogeneous. Other structures, small folds, offsets, breccias, like big aragonite fragments that haven't been broken up completely, micro-breccias, or these huge mass movement deposits, and large clasts, this very large pebble. And some of these MMDs, mass movement deposits, are very thick, more than 1 meter, 2 meters, 3 meters. The biggest one is 6 meters thick. Here's a nice class that stayed somehow in one piece. But if we look in the, let's say, for example, zoom out a little bit from those pictures, but here's just an example of a 7 meter picture of the core, 7 meter section of the core, just to show how ubiquitous these events are. We have here, I had the number here, I don't remember, but there's at least 5, 6, 7, 8, 9, 10 per meter in this picture. A little bit less, more down here, bigger ones up here. There is almost 10 times more in number, more of these events than what we see in the margins. The seismites that we see in the outcrops, if we're comparing them to seismites. So, a comparison in the meantime. So in the margins we have mostly these millimeter scale laminates, AD, gypsum, some thicker detritus layers, max 2 centimeters, interpreted to be earthquake-induced interclass breccias, faults, association between breccias and faults in the field, and this is a 30 to 40 meters. At the depocenter, as I said, between 90 to 110 meters thickness, more or less same looks like in the meantime. But what we don't have in the outcrops, or only one, is one huge convoluted layer, many thin homogenites, while in the depocenter we have 14 mass movement deposits that are larger than 1 meter, many thin and thick homogenites, and hundreds of these turbidites and semi-turbidites, homogenite type events. Okay, so could these, let's talk about the homogenites, the centimeter scale homogenites, 5 centimeters, 10 centimeter scale ones. Could they be flash floods? Could the sediment be just a huge flash flood, huge floods depositing the sediments at the depocenter? So from modern studies of the floods, they don't seem to move very far. For example, this study in Hawaii 2013, they're just studying 2 sites, one 5 kilometers offshore station and one coastal station, measuring the turbidity of the water after a flood. And they show there's a huge difference. The 5 kilometer offshore station barely notices this flood. There's a small, tiny peak here and another peak here. No reason to believe that this flood would supply enough sediment to make, obviously, there's less sediment supply during these floods to the center than there is to the shore, not more. This is just a modern analogy. So we have the 60-meter Lisan addition of allochthonous material, it seems. The thickness range per event, 1 to 2 centimeters to 600 centimeters. As I said already, 14 of these very thick ones. And why so many? So the marginal breccias, we think it's more of a local disruption. An earthquake occurs at the site. The sediment is resuspended into the water and redeposited at the site, liquefaction at the site. There could be small movements, but it doesn't move very far. The slope is very flat. And at the depocenter, we have local disturbances. If it's possible to even cause liquefaction under such a thick water body, we're not sure. But it definitely will receive material from any unstable structure that fails in the area, getting material from every different direction. And why there's so many, what they mean, is open for discussion. But I'm going to show you another sort of modern analogy. But we're in a pretty flat abyssal plain. the tectonic basin, the sediment supply. It seems to be this plane is being buried very quickly. It's very flat. There's almost no lineaments. Mass movements, turbidites could be very effective mechanism for transport in covering up any tectonic structures. And all this has implications, of course, is the depositional basin. Now, the Lenski, Nadav Lenski, studying the modern coastline of the Dead Sea, of the retreating shores, is showing that the shores are more and more jagged as the lake recedes. And they have shown that these are scarred slopes, that the scars are being exposed as the lake recedes. This is the topography, the bathymetry at these different depths over here. Here it's very sharp topography over here. And they're showing that these are scars of mass movements in the current bathymetry. And of course, this stuff has to go somewhere. Whatever's being cut out of the slopes has to be found somewhere at the depocenter. So the average scar depth per length unit, 30 meters, average. And according to very simple calculation, their calculation of a cut and fill, if we have a 4-kilometer area where these scars exist and 30 meters average cut, and assuming that this sediment is being deposited on this area, which is, let's say, 8 kilometers long, flat depocenter area, we would get, if these scars, if these events happened at one time in one event, you'd get a 15-meter turbidite, a 15-meter mass movement deposit. We don't see anything that thick, and there's no reason to believe that each one of these scars happened at one event, and this is also very averaged, but it's just an analogy, and also these scars are, happened during the last hundreds of years, thousands of years. It's definitely during the Holocene, and what I'm looking at in the cores as Lisan, so it's just a comparison. It needs to be modified for an assumed lake Lisan configuration. Things were different, but it is interesting to look at. So as I said, one event would create a 15-meter thick turbidite, and we don't see this. We see 6 meters at most. And if we're still using this analogy, we'd get about a third of the volume of the scars seen today for a 6-meter event. That's how much we'd need. To make a 6-meter turbidite, we'd need about a third of the volume of what's missing in these scars. We need that to move for one event. And of course, it's a continuous process of many discrete events as well, small ones and big ones. And we also aren't always seeing necessarily the slide that happened directly, in front of our core sites, and these thin turbidites make tails of more distant events. Of course, what's missing here in this whole campaign is a transect of many cores. Like most of these studies that study turbidites in cores, they have a transect of 5, 10, 20 cores, and then you can really follow them, each one, and that would be nice, of course. But we don't have it. So what we do have is this core, and so this is a percent of each core interval. This is divided, this is not time, this is core intervals, top to bottom of the Lisan, 14,000 more or less, to the bottom of the Lisan. This should say 70 now, according to the new chronology that's already accepted in EPSL. And each core, how much percent of the thickness of this core is massive, is not laminated. And massive, I mean one of these kind of events, turbidite, homogenite, fold. So we see some of them are 100%, obviously the ones that are 6 meters thick, they take up 100% of a few of the cores. As you can see, every one of the cores has I think the the lowest number here is about 38% of one of the cores is massive. The rest of them have more. So in total, more than 75% of the Lisan thickness is mass movement or highly deformed. Which fits in with more or less with what we see just by comparing the thicknesses of the marginal outcrops and the depocenter thickness. And here I put the depth of the location of the really big mass movement deposits, in which core they are. Another comparison. Some of them we saw already. 5 to 10% of the thickness in comparison to 75% of the thickness of the core. The margins, resuspension and resettling, as opposed to what we think is the main mechanism, the depocenter mass movement. The margins usually preserve delicate features, and in the depocenter, not many of the original features are preserved. There's some of these folds that are nice, but most of them are not preserved. Seems that they were transported. Did not add, in the margins, it didn't add much to the thickness, these size mites. And the depocenter of these events add significantly. Erosion, in the margins, it seems like there was not much erosion. Like what we're seeing, the whole section is there. Some of it is resuspended. And in the depocenter, we don't know if there has been erosion or not. Very detailed dating, which it's not going to happen, could give if we really had a date every 20 centimeters, we might be able to say more about erosion. For example, when one of these mass movement deposits arrives at the depocenter, does it cause erosion, or is it just adding material? If we had a date, immediately below a mass movement deposit and immediately above, which is possible, just not at every single one, that's one of the next stages of the project, then we could say something about if there's part of the section missing, or it's just there's just section being added.
So compaction, have you integrated compaction?
I haven't. We haven't taken it into consideration yet. That would mean that the section was actually even thicker.
Yes.
It would just.
Especially the level.
Okay, so here we can see the outcrops, the cumulative sedimentation. The red diamonds are ages, uranium thorium ages, published. You can see more or less continuous sedimentation, not much change in sedimentation rate. Here, there is a hiatus in Masada, and at Mishmar, in Masada, this blue triangle here is a big convolute layer, like a big mixed layer that, is maybe 1 or 1.5 meters of section that we think was, it happened, an event, it happened immediately, so it kind of changes the H-depth diagram. So this is thickness and this is age. I don't know if you can see it, 70,000 years ago to 14,000 years ago. And when you compare this on the same scale, to the same thickness scale, to the deep core, you see that we can't draw a straight line anymore. I just put into this, we don't have very many ages from the Torpstein paper, accepted paper. I don't even think he uses all of them in the paper, but these are ages that he also gave me an extra one. Can't draw a straight line anymore because every single one of these events that is bringing material from another place is being deposited in one day. So we have to have these, these steps in the H-depth diagram. This is where I just added the ones that are a meter and more. I have to, if I put in every single one of these mass movement deposits, it would look different. I mean, the really small ones you wouldn't be able to see, but these steps or these jumps over here are the largest mass movement deposits. And there's just a little arrow. This is the same picture. And obviously this has implications for the precise dating of short climatic or paleomagnetic or limnological events that the majority of the campaign team is working on these very short and very discrete abrupt events in mostly in the climatic record, and not really, they're not really taking into account the mass movement deposits, which take up, as I said, 75% of the core. So this is serious implications for the age depth diagram, and whoever wants to look at the fine details and know when they happened. As I said, there's this one convolute layer, and really, almost amazingly, in the Mishmar and Masada outcrop, they gave the same age on the age depth diagram, and this layer wasn't used as an anchor or anything in creating the age depth diagram. And in the depocenter, there's also a very large mass movement deposit in it. There was a plus minus of about 1,000 years here, but it's just quite amazing that it comes out to be almost the same age. And they weren't used in tuning the age depth diagram, as other geological markers were, the gypsum layers, etc. And this is the lake level, Lisan lake level, really just taking a look to see how the large mass movement events look if you put them, at the same time as the lake levels. And I wouldn't say I see a real correlation. And some of the lake levels drops or rises are so short that really you have to make sure that the core chronology is better defined. Because on the shores, they're really well defined. And here, if you look at them, if I look at these, this doesn't take into account how many mass movement deposits there are. I just put on the big ones. Not necessarily size matters. Maybe we should put on, I'm going to add to this also the frequency, the occurrence of these events. I personally am not sure. I see some of them happen in high lake levels, low lake levels. As I said, more of them in low lake levels, or this is high lake level, but during a low event, there is I could think of quite a good explanation of why you'd have more events during low lake level. Well, there's more sediment is exposed all of a sudden and could be more susceptible to earthquake. Lower lake levels on fresh sediment could increase the possibility of it being disturbed by the earthquakes. But I wouldn't go that far just yet. So that's a review. I'm not going to review all of it again, but the sun is much thicker. 75% of it is from somewhere else, not laminated, regular lake lamination. There's up to an order of magnitude more of these deformed layers in the core than the same time period at the margins, suggesting slumps, slides, brecciation, turbulent flow from many parts of the lake that could reach the epicenter. The submarine slides are apparent in the modern topography and bathymetry. This could be an effective transport mechanism, and maybe thicker mass movement deposits during low lake levels. And as I said, the high resolution ages are critical. To be continued is high resolution dating. As I said, maybe right below and above to a deposit to understand more about erosion. And to correlate, to work on the shallow core. As I said, there's also a shallow core from this campaign. It was tempting everybody's working only on the deep core because it's just so different than what we're used to. The shallow core is not that far from the outcrops that we know, but still it is closer to the hinge line of when the lake gets deeper. And I'm sure, just from looking at it briefly, there are also a lot of these disturbance events, and we're working on starting some kind of sediment transport models and subsidies. Have to get to that, and we'd love to see soon, one day, high resolution seismics, which is also, of course, in most studies of turbidites, very important, and can give us a more of a 3D view of what's going on, because we're really 1D right now. And that's it. Thank you very much.
Okay, thank you very much, Lisa. Any questions, please? Yeah, Uri?
You totally ignored any sources on the east side, both climatic, flooding and some earthquakes, having very steep both above water and underwater slopes. There, as you can show the flooding and the suspension, resuspension of sediments and stuff like that. And of course, since sitting in the middle of the lake, immediately you could say, even if you did not know anything, you'll have sources from both sides, you'll have double, and you'll have just on the western side, without anything else, not knowing any other information. Did you try and make any estimates at all, either from an earthquake point of view or from climate, which was very wet and eroded the eastern highlands a lot more extensively then than it is doing now, as to what you would expect to find in the earthquake?
Well, if we didn't ignore it completely, but if the source of this thickening of the sediments was that the regular silty laminations were thicker, then I would talk about sediment sources from floods from the east or from somewhere else. But as I said, 75% of the thickness is not laminated, is disturbed, and seems to be coming from mass movement events. On the east shores or slopes are very steep. There doesn't seem to be much sediment accumulation there. The sediments seem to be there aren't scars that the same what the Lenski study is showing, that there's no scars there. The sediment's not staying there and ready to slide. But that has to be dealt with about the slides. And as I said, I don't think the slides are all coming from these slopes that are directly in front of the core. We don't know where they're coming from, and that's one of the options that we gave for why there's so many more events than what we see in earthquakes. Assuming that a lot of them are earthquakes, we are in a seismic tectonic area near the faults, we would assume that yes, local earthquakes, smaller local earthquakes that did not cause seismite to form in the Masada plain, but an earthquake, let's say, on the eastern shores of the Dead Sea or somewhere else might have caused a seismite there. We don't see the seismite on the western shores, but any event like that would bring some kind of allochthonous material to the depocenter.
So even as far as the silt, if you remove all the landslides, what the thickness of the layers, the undisturbed layers, in the lake versus the one in the sun? It is short.
The thickness of just the laminated section?
Yeah.
The laminated section, as I said, 75% of, let's say if we want to take just the 70,000 to 14,000 year interval, 56,000 years, thickness. So we have from 90, the lower level, it's 90 meters, 75% of the 90 meters. It's still, you want to know if it's more or less than at the margins?
Right.
It's less, definitely less than at the margins. It's still, even the laminated is less than at the margins, less than 20%, 23%, something like that. Meters, sorry.
Which makes sense.
25% of 90 meters. We're having the laminas, you can see just by eye, and also work that's being done by other people working on climate. Just the thickness of the lamina are slightly thinner in the cores than known from the core, from the marginal cores.
It's about 30 meters that is laminated, according to the calculation method, in the bottom compared to the laminated sequence on the margins, which I think makes sense because in the margins you have all the sediment coming with the hydrological system, and at the sink, at the middle, you will only have the big flash floods that are bringing sediment or the sides.
And you have also, it's a short, transport, and very steep transport thing, so you have less of a chance to actually build, but that again, the short transport is from both sides, is a real.
I have definitely had no problem with receiving Jordanian sediments. So it makes sense to me totally, and especially, earthquakes, everything. As I said, that's why we think there are many more events seen
Is there
in
something
the
in,
deep
in
shore.
the mineralogy that you can tell?
Yeah.
In the mineralogy of the core?
I don't know, I thought, I
The
think
geology,
Elisa is working on
the
this
geology,
also.
we didn't see anything special that could be distinguished, but I think if a systematic work will be done on the core, on the mineralogy, using all the XRF data, there is a big difference between the mineralogy of the Israeli side, which is mostly carbonate, and the
However,
and the Jordanian side, which is sandstones and basement.
however, the
silicic
question
matter.
is that what the floods are bringing? The floods, according to most people, are bringing mostly dust.
Well,
Mostly settled dust, okay? I
that's
don't know.
another discussion, yeah.
So, you have to first know if the floods from the eastern side and the western side are bringing mostly, or I don't know, what percentage. It's not all of it broken up, granite and as opposed to limestone. It's a lot of it is dust, soil, etc.
So you have people doing palynology or nobody?
There's, for sure, there are, and it's the first Lisan palynology study ever, because in the Lisan on the outcrops, as far as I know, maybe I'm missing something,
משהו
but
ברור, הוא
there's
ברור.
no, the pollen has not, it didn't remain in the outcrops, correct? Oxygenated? So now there's at least three students of Thomas Litt from, where's he from? Bonn. Thomas Litt from Bonn is at least three students, if not more, working on the cores, and one is, at the Engedi conference, she gave a talk about the Lisan pollen, it was still low resolution, depth-wise study, but
Did you find something?
yeah, there's pollen and
We
the
are
whole
also
section.
working on the pollen from another point of view. We are looking at it's work with Susan Leroy, I don't know if you know her. We are trying to distinguish between pollen that is by the taphonomy of the pollen, to distinguish between the pollen that is brought by flash roach, which is very recycled, and pollen that is airborne, and you see differences.
I think one of the problems is that most of the people working on the core, not on these mass movement deposits, when they only took samples from the laminated section, like all the people working on pollen or anything, even the XRF, the general XRF that they did on the whole core, they stopped it every time they got to a mass movement deposit, they stopped it. So, this was done immediately after the core was opened, and then, and I'm not saying it can't be done, but most people, they just wanted to take what was, definitely local deposition, and they wanted to.
Okay, Nadina?
So you think most of the material that you find in those homogenites, let's call them, is reworked or is actually really brought in? Do you have any idea on that? Because 23% lamination compared to the outcrops seems to be really low.
You're saying that the laminated part of the Lisan is is much smaller than on the margins, and why is that? I don't know. It could be erosion, as I said, but I don't know. And also the thinner silt, the less amount of flood deposits reaching the depocenter, even if it's coming from both sides. Most of the sediments are deposited close to shore.
Okay, Yossi.
Do you have any evidence of anoxia?
I'm not working on that. I don't know. I'm not sure. I don't know about that.
75% of the core of the Lisan makes it larger by 75%. Did you by any chance see any of those things in other parts of the core?
Yeah,
or
the
you
whole
never saw
core.
them?
Yeah, just the Tselim, just the first. Sorry.
I'm not talking about only the Lisan part.
Okay,
Yeah.
the Tselim formation, Holocene. It's like that. The whole. That's what I started basically the lecture with, saying that everybody thought we'd be going much back further in time with 450 meters of core, and because all of the section is, as they call it, menupach, is enlarged, is thicker than we thought. Sorry, hold on. Where did it go? trying to talk and you guys at the same time. The saline formation at the margins is about 20 meters, okay? Saline formation, Holocene, until you get to the main salt below the Holocene or at the
And in the core,
Pleistocene, Holocene. And in the core, it's about 60 meters. Here. I mean, you have to take a lot, it's not just a simple calculation because we have a lot of salt deposition in the cores, and the salt also enlarges, thickens the section. But just till here, there is quite a bit of salt up here, but still, didn't work on the Holocene, but it's quite a simple calculation to just count the thickness of the salt and maybe remove it from the calculation, from the addition, and it gets all the way here to 70 meters. Saline formation, much thicker. And some, I don't know exactly what it is on the margins, but this is, the whole thing is much thicker than expected from.
do they look the same? Sorry. Do the turbidites or whatever, the mass movement,
Do they look the same in the Holocene?
throughout the core? I mean, some as well, I suppose.
Well, that's why, no, definitely don't look exactly the same. In the Holocene, they're just much harder to recognize, I think. They're not so different, but because the Holocene normal sedimentation is much siltier and less aragonite, laminite, it's not so extreme, the difference between these homogenites and the Lisan and the Lisan type, and the regular, laminated detritus that you see in the saline section. I mean, this is, using, under a microscope, I'm sure it's quite easy to differentiate between a silty deposit and homogenite in the saline as well. And I think Elisa, maybe we'll talk about it in 2 weeks, she's talking here. But no, they don't, there's not so many of these huge folds and
Okay, we have time just for one question.
I'm not sure if you have the answer, but I wanted to ask if you know about maybe the younger parts, or if there have been events that were correlated to catalogs or known earthquakes that happened.
I don't have the answer, but I know that it's not, we're not there yet. I mean, there's just so much work that I don't think anybody's working on that right now. Of course, I'm aware of this subject, and it's close to heart. I worked a lot on the shores in the saline section as well, and correlating to historical earthquakes, but I don't think anybody's working on that right now.
Did anybody look at all at the salt to see if the salt is all simply deposited in place, or is the salt as well going through?
The salt, there's a lot of people working on the salt. I can promise you that, because it's something that we don't really have on the margin. So it's exotic, and everybody wants to work on the salt, and lots of fighting going on. Who's going to work on the salt? Thank goodness I'm not involved in this one. So there's already a paper written, like this main lithological paper, where we're also describing the different kinds of salt, and a lot of the salt is laminated, but there is one kind of gravelly salt that no one's really explained yet why it's this, Yeah, it's a possibility that some of the salt was also transported. Assuming, let's say, earthquakes cause these mass movement deposits, some of them at least, of course, if there's salt exposed, whatever's exposed is what's going to slide. Some things maybe are more susceptible to sliding and some things less, but you're not going to get something sliding that's not exposed. Unless, of course, if you have a big chunk coming out, then yes, everything will be deposited in the middle. But basically, most of the salt is laminated, and there are some salts that are suspicious of being transported. And there's other interesting things, like at the top of the, between the Tselim and Lisan, there's this kind of AAD, this laminated aragonite, the detritus part that doesn't seem, the people working on the climate are asking me, do I think it's transported, because it doesn't kind of fit in with what they know about the climate, so they all of a sudden want to know if maybe it's out of place if it was slid into there. So,
Okay, thank you very much.
הנורמליות באנו, עמית,